Please see the video description for a full list of disclaimers, including the ones here, plus a timeline and helpful resources and links. Please support the channel by using our affiliate links.
Recently, we looked at an interactive web simulation that lets students or other users manually adapt modulation and coding scheme in a fading channel with the goal of maintaining as high a data rate as possible and transferring as many bits as possible during a timed interval. Today we'll look at the next simulation in the hands-on learning for radio frequency spectrum innovation, or HLSI series, and now we're getting into automated adaptive control of radio links. Not only will students be able to run and compare different adaptation algorithms, but they'll also be able to modify the algorithms or replace them with their own code. We'll take a quick look at the user interface, although much of it is similar to what we saw in the previous simulation. First, as in the previous simulation, we have a spectrum plot, a data rate or throughput history plot, and a spectral efficiency plot. In this version, the power spectral density plot does not have the 3D option, but that will not affect the way that the simulation is used greatly. Also, we have a few notes on the meaning of some of the variables that are used in the adaptation code. The adaptation code can be seen in this text box in the upper left of the simulation. And below that, there's a menu that lets us select from among multiple pre-coded adaptation strategies. These include random selection of modulation encoding scheme, an algorithm that checks whether the link is closed, another one that checks the link margin, and another one that is intended to find the best scheme. And we can see what each of those looks like. If we click on one, the text box will populate with the code for that algorithm. The first one actually uses a fixed modulation encoding strategy, so we could select any of those schemes and compare their performance in a timed simulation. So we'll start by selecting the fixed modulation encoding scheme. Then we'll see that there's a button here labeled Go that we use to start the simulation. And as we saw in the previous simulation exercise, there's a row of text-based feedback that includes things like SNR, theoretical capacity of the channel, spectral efficiency, link margin, and the actual data rate achieved with the selected MCS and the percentage of the theoretical capacity that is achieved using that MCS under the current operating conditions. There's also a line here that shows the time left, 600 in this case, the number of outages, and the total bits transferred. The number for time left is not strictly in seconds, but does give a relative view of how much time remains in the simulation. When we select Go, we see that the channel simulated here is a fading channel in which the amplitude of the signal, or its power spectral density, changes over time. And that affects the power spectral density that is achieved using a given modulation encoding scheme. The algorithm that we're using just selects a particular MCS and does not adapt it to changes in SNR that result from the signal fading. As a result, the link is closed when the fading is minimal and the signal is strong and the SNR is high, and the link is not closed at other times. We see that in the data rate history plot, which shows some outages and some periods of constant data rate, giving it the general appearance of a square wave or a pulse train. In the interest of time, we'll just try one of the additional algorithms and make a minor modification to that algorithm. After that, I'll encourage you to try the simulation on your own, whether you're a student using it in a class, a professional taking a CEU course, or an independent learner who's using this in your own exploration of wireless concepts. Also, if you're in an instructional role, if you're in some other kind of workforce development role, you're also welcome to try this simulation and use it and even modify it because it is open source code available under an MIT license. From our menu, we're going to select Check Link Margin, and this will check to see whether and by how much the SNR exceeds the minimum SNR for the selected modulation and coding scheme, and decisions on adapting the MCS are made based on that information. We'll go ahead and run the code as is first and see how many bits we're able to transmit during the simulation. Last time we were at about 509 million using a naive approach that used a fixed modulation and coding scheme. So here we're going to run the simulation by pushing the go button. We see the data rate, we see the total number of bits incrementing. There are some outages, although for the most part we can see that the operating point is following the empirical limit on achievable data rate. Sometimes it goes past that threshold and into the red area, and so as a result there are some outages. We see those clearly in the data rate history throughput. We also see that as the signal becomes stronger, the data rate is increasing, and as the signal becomes weaker, up to the point where it's no longer possible to adapt sufficiently, the data rate gradually decreases, with a few dropouts here for cases in which the decision is not made quickly enough to avoid an outage before selecting a more robust modulation and coding scheme. We're going to make a minor modification to this algorithm and see if we can improve performance. So note that in this case, about 1.357 billion bits were transmitted and received successfully. So 1.357 billion is the number to beat, and we're going to see if we can make some improvements. Now, if you're just in case your algorithm becomes longer than what will fit in this text window, you can see that you can grab and stretch the window by clicking on the lower right of the window. We're not going to need much more space here, so we don't really need to do that. We will use the Control+ control sequence in the browser to zoom in so we can see that algorithm a little better. Okay, so what we're doing is checking for a variable called L margin, which would be link margin, presumably in decibels. It actually is listed in our list of variables, so let's assume that that's in decibels. If the link margin is greater than 4, what we're doing is returning the current MCS plus 1, because whatever value we return is the index of the MCS. The higher indices represent more aggressive combinations of modulation and coding. And so we will be increasing that if the link margin is high enough, and then decreasing it if the link margin is less than or equal to 1. And if it is greater than 1 but less than 4, or up to 4, then we will maintain the current MCS. So we're going to make this a little more conservative to avoid the dropouts that we've seen. And what we'll do is just require this link margin for increasing MCS. We'll just change that to 5. So we've adjusted that threshold. We'll change this other one to 2. And let's zoom out using Control- and rerun the simulation. Okay, again, the number to beat is 1.357 billion. And here we go. Okay, so we see there's still cases where there are dropouts or outages, and that's because it's not possible to close the link using any of the available modulation and coding schemes under the worst case fading that is presented by the simulation. But we see that those outages are relatively infrequent, and because the outages are fewer, perhaps we've managed to transmit and receive more bits. But no, it looks like the number here is 1.28 billion. So we've actually slightly decreased the total number of bits transmitted. We may have reduced the number of outages. You can look back at the video and see whether we've reduced the outages, but we haven't improved the total number of bits transmitted. but you can try to beat this. And in some cases, it is possible to improve on some of these algorithms. You'll just have to explore and see how best to do that. Thanks for your time. I hope that you found this video useful. If so, please like it, give thumbs up, subscribe to the channel if you're interested in seeing our other videos on a variety of wireless and research related topics. And as always, please feel free to pass on the video or link to the video to any colleagues or students or anyone you know who you think might be interested in seeing it. Thanks a lot, and we'll be back soon with another of the simulations in the series. I look forward to seeing you then.
Thanks for your time. Please hit like and subscribe and support the channel by using our affiliate link if you plan to buy a featured item. We also provide consulting services and referrals.